I'm going to teach you alkenes, alkynes, and aromatic compounds. So to begin with, if you haven't watched our alkane video yet, make sure you go check it out and make sure to subscribe to us. But if you've watched it, then you're ready to move on to the next video. The first thing I'm going to be talking about is saturated versus unsaturated compounds. If you've watched the alkane video, you'll realize that they're saturated compounds. You have no functional group, because saturated means that the compound does not contain a double or triple bond. All the carbons have single bonds. An unsaturated compound has double or triple bonds. For example, alkenes and alkynes, even aromatic compounds, they're all unsaturated because they have double bonds or triple bonds in them. Whereas alkanes are saturated. They do not have any double or triple bonds. So now that that's out of the way, we're going to go on to naming, because everybody loves naming organic compounds. So right now we're going to start off with alkenes and alkynes. And then we're going to move on to aromatic compounds later on. So firstly, that didn't happen. We're going to start off by naming the very first compound I drew. As you can see, it has a double bond. So that makes it an alkene. And if it's an alkene, we have to use the ending of alkene, which is ene. So this is going to be our suffix for our nomenclature. And I have two carbons. I have 2 carbons in my compound. So 2 meant F. So if I write F, and then I have the ending E, I get my name. It's as simple as that. What about that other one? Well, this is a triple bond. Triple bonds mean alkyne. Now alkyne end with Y and E. So I already know my suffix. It's going to be Y and E. Now, how many carbons? 1, 2. I have 2 carbons, and 2 carbons meant F. So this is going to be ethane. It's as simple as that. There's nothing hard about it. Alright, now it gets a little tricky. Look at this. I do have the structural formula. And as you can see, it gets pretty confusing. So before we name this, I'm going to try and make it easier by first drawing out the line formula. So, first of all, we can see there's 5 carbons in a ring. I'm going to draw that out. So there's 5 carbons in a ring. And between the top 2 carbons, we have a double bond. We have a double bond there. And we have a methyl group attached over here. So I'm going to draw a line there. That's our line structure. Now we're going to go on to naming it. Well, we studied cycloalkanes in the previous video. In this video, we have a cycloalkene, because it's a cycle, it's joined together, and there's a double bond in it. How am I going to name this? It's very simple. First of all, you take the longest alkene, which is, as I already mentioned, 5 carbons. So this is going to be a pentene. And since it's a cyclic compound, it's going to be cyclopentene. So let's start off with writing that. Cyclopentene. However, we have to mention the methyl group somewhere. So naming it isn't complete yet. The next point we have to do is we usually label the compound to see out which of the numbers are going to be least for any substitution groups in it. For any alkene or alkynes, we have to start, any cycloalkenes or alkynes, we have to start the double bond at position number 1. It's a rule. So this, even though it would be so much easier if you made this position number 1, and then you just write 1 methyl cyclopentene, the double bond has to be included as position number 1, because the double bond could actually be here, or here, or here, or here. The double bond itself has a position. So we can't just namely state that, oh, this is on this carbon or it's on that carbon. We have to specifically say which carbon the double bond is at, and which carbon any constituents are at. And therefore, to make life simpler for us, any double bond in a cycloalkene or a cycloalkyne, we have to label the double bond or triple bond as the first carbon. So if we start clockwise, 1, 2, 3, 4, 5. So if we go clockwise, we get the methyl group at position number 3. What if we go anti-clockwise? 1, 2, 3, 4, 5. If you move anti-clockwise, the position comes at, the methyl group comes at position number 5. So obviously that is incorrect. We want to take the least number, and so we have to move in a clockwise direction, leading us to 3 methyl. So it's 3 methyl cyclopentane, a pentene. 3 methyl cyclopentene. Let's move on to something a little bit tricky. Now over here, I drew out the structural formula again, as you can see. So what we do, we take the longest chain of carbon to see how long the compound is. Well, 1, 2, 3, 4, 5, 6, 7, 8, 9. Obviously, the longest chain is 9 carbons. However, the other chain is 1, 2, 3, 4, 5, 6, 7 carbons here. We have to take the 7 carbons as our longest chain. But why is that? Because the 7 carbon chain is the one that includes the double bond. You have to include the double bond in your longest chain. If your longest chain does not include the double bond, as in this case it was a 9 double chain, it's not a compound then, because we don't have a name for a double bond constituent group. We only have names for this. This is propyl. We studied this in a previous video. But if you have a double bond, we don't have a name for that. That's why we have to include the double bond in our longest chain. So this is not actually nonane, but it's actually heptene, because it's 7 carbons. And it's an alkene. So I have to write heptene. Now, what position is the propyl group? The propyl group is at position number 2, if you start this way. 1, 2. And that's the better way to start as well, because we have to, like I said, like I mentioned in this example, we have to mention where the double bond is. In this case, double bond is at position number 1. So this is going to be 1 heptene, 2 propyl. So 2 propyl, 1 heptene. That is the name of your branching alkene compound. So, and these rules apply to alkynes as well. However, number 5 and number 6 is exclusive to only alkenes. This example only needs, the next 2 examples, 5 and 6, only happen when you have a double bond. They will not happen anywhere else. And this is the cis and trans isomerization. What do I mean? The double bond cannot be rotated around. I gave you the example of rotation around bonds in the alkene video, when I call those conformers. In this case, you cannot rotate around a double bond. It's impossible to rotate around a double bond. So whatever is stuck at the top of a carbon will forever remain at the top of the carbon, and whatever is stuck at the bottom will remain at the bottom. That's why we get 2 sorts of isomers when we have different groups on the carbon. If this was all the same group, it wouldn't matter. For example, if we had ethene, it wouldn't make a difference. But if we have 2 different groups on both different carbons, this is where the isomerization can come true. So I have a methyl group here, and I have a methyl group here, and I have a methyl group here, and I have a methyl group here. In this case, they're on the same side, and in this case, they're on opposite sides. So obviously, although their formula is the same, their structural formula is different. How can I use this how can I put this in my name? Well, firstly, I have to see the longest carbon chain. This is 1, 2, 3, 4. This is a 4 carbon chain, so this is butene. I know that. And the double bond is at position number 2, so this is 2 butene. So let me write that down. 2 butene. However, this is what we call cis butene, because both of the carbon groups on the same side. So this is going to be called cis. And this one, although it's also 1, 2, 3, 4 carbons, and the double bond is at position number 2, so this is also 2-butene. We can call this trans 2-butene. And that's because the carbon groups are on opposite sides. So now we've done all our naming. If you've got any questions, you can do some practice examples, and you can send them to us for checking. As for the properties of alkenes and alkynes, they're non-polar because they don't have any extra electronegative elements. They're flammable, just like alkanes. Almost all organic compounds are flammable and can undergo combustion. But the thing that makes us different from alkanes is that they're very reactive at their functional group. And that's because they have a double bond or a triple bond which can undergo some sort of reaction. And the main reactions that they undergo are addition reactions. And the two main addition reactions are hydrogenation and halogenation. We also have hydration, but there's something specific about that I will mention in a bit. Alright, now we're going to start off with the reactions. So as I mentioned, one of the main reactions they undergo is addition reactions. And the first one is hydrogenation. This is hydrogenation, this is halogenation, and this is hydration. In hydrogenation, what happens is the double bond opens. So when one double bond opens, you get two other bonds, you get two free electrons. Just think of a double bond as two hands joined together. This is one electron from one carbon, this is another electron from one carbon. When you break this bond, you get two hands, which can then make two more bonds. So breaking one bond does not necessarily mean you can only form one new bond. Breaking one bond could mean you can make two new bonds, as in the case of covalent compounds. So when these two bonds open up, one H will go here, and the other H will go here. So what happens is, you get a compound like this. And that is hydrogenation. It's the same concept with halogenation. You break the bond, the bromines come here, and you get a compound. For example, this is what's going to happen. For hydration, it's the same thing. The bond will break, double bond, and H will join on one side, and an OH will join on another side. So, this is what's going to happen. However, hydration isn't as simple as that. You get a little bit more complicated when you bring in a factor called Markovnikov's rule. You thought your name was weird? Well, listen to this guy, Markovnikov. Okay? Now, what he said is a very basic principle. He said that the rich get richer and the poor get poorer. Anything with hydrogens will get more hydrogens, and anything with less hydrogens will not get hydrogens. What do I mean by this? Let me explain. So, if I have a compound like this, this is propene, and you can get two different products with this if you react this with water. You can get a product like this, and the rest are hydrogens. I'm not going to draw those out. Or you could get a product like this. and the rest are hydrogens. I'm not going to draw them out. Because when a double bond breaks, you get two single bonds, which one H can attach here or here, and this OH can attach here or here. So depending on where they attach, you can get two completely different compounds. But which one of these compounds will be formed more? And the answer is this one. Reason being, this carbon has two hydrogens on it. Use a different color. It has two hydrogens, whereas this carbon only has one hydrogen. Like I said with Markovnikov's rule, the rich get richer and the poor get poorer. Because this thing has more hydrogens, it's going to accept another hydrogen. And because this thing has less hydrogens, the non-hydrogen part, the hydroxyl group in this case, will then go to the part that has less hydrogen. You can use the same principle for the addition reaction of, let's say, HCl or HBr. You can try that out, and you'll see it comes out with the same thing. Anything that has more hydrogens will accept more hydrogens, and anything with less hydrogens will accept the non-hydrogen part. For example, in this case it will be chlorine, and in this case it will be bromine. That is hydration and Markovnikov's rule. The last reaction is polymerization or polymer formation. What is that? Let's say we take an alkene, a very simple alkene. We'll take ethene. Now if ethene and an ethene come together, what can happen? This double bond can break, forming two bonds, and this double bond can break, forming two bonds. Now these bonds can join together, leaving you with a 4-carbon product now. Let's say you had another ethene here. If you had another ethene, this double bond could break, giving you 2 bonds. This bond would join, and now you have 6 carbons. And as you can imagine, you can keep on going and going and going and going. Now, we call these polymers because you can take an alkene monomer and you can keep on multiplying it again and again and again and again. Now, in this case, this would be called poly, because it's many, polyethene. And you guys have probably heard of polyethene. Another example of polyethene is also known as polyethylene. Polyethylene is an example. It is the more common term we use nowadays. Although the correct naming is polyethylene, polyethylene is a name that's been going on for quite a while, so we stick to that. So that concludes all the reactions we have for alkenes and alkynes. Now we're going to move on to aromatic compounds. Now we're going to be talking about aromatic compounds. Aromatic compounds are called aromatic compounds because they have a benzene ring. Now, as you can, a benzene ring is a 6-carbon ring, 1, 2, 3, 4, 5, 6 carbons in a ring with 3 double bonds. However, the double bonds could be oriented this way, or they could be oriented this way. So which one is correct? We actually don't know which one is correct because the double bonds are always shifting in this case, and that's why they produce an effect called resonance. And we represent resonance as drawing a hexagon and then a circle in it, meaning the electron cloud is dispersed throughout. If you're confused, you should watch a video on hybridization. Now, I got some things down, and we're going to name 2 of these compounds. 3 of them are already named, but we're going to talk about those in a minute. Now, this is a very simple compound. This is, as many of you know, this is benzene. What about this? This is a methyl group attached to a benzene. So this is going to be methylbenzene. But which number is it going to be? It's going to be 1, 2, 3, 4, 5, or 6. Because if you remember, when we were talking about cyclic alkenes, they also have a double bond. We have to include a double bond as number 1. But in aromatic compounds, this is different to an alkene. This is 3 double bonds that have resonance. In a in a cycloalkene, you don't have resonance. So we have to include it as number 1. And for the example of an aromatic compound, you don't. So this constituent will be number 1. So this becomes 1-methylbenzene, or in that case, just methylbenzene. Now, as you can see, I've drawn out 3 different types of dimethylbenzene. 2 methyl groups attached to the benzene. But there's a difference in all of them. This one is, if you label the carbons 1, 2, 3, 4, 5, 6. This is 1, 2 dimethylbenzene. This is 1, 2, 3, 4, 5, 6. This is 1, 3 dimethylbenzene. What about this one? This is 1, 2, 3, 4, 5, 6. This is 1, 4. 1, 4 dimethylbenzene. However, we have some special names for these specific numbers. If there's a 1, 2, we call this ortho, and we represent this with an O. So this would actually be O dimethylbenzene. For a 1, 3, we call this meta. So we represent that with an M. This would actually be M dimethylbenzene. And if something is 1, 4, we call this para, which we represent with a P. So this would be P dimethylbenzene. And that's all there is to naming. Now on to reaction. Alright, now we're going to be talking about the aromatic compound reactions. Now the main reactions you undergo are substitutions, not addition reactions for some reason. Although they have double bonds, so just like alkenes and alkynes, they should undergo addition reactions, but they don't because of their resonance. Because they have resonance, they're actually much less reactive than alkenes and alkynes. And the only reactions they will like to undergo are substitution reactions. For example, of course there are H's everywhere here. I just drew out one H for clarification. If I combine it with a chlorine molecule, what happens is this chlorine molecule will substitute with this H, producing a compound like this. What about if we take a water molecule? If we take a water molecule, this OH will combine with this, leaving a molecule like this. What about if we combine it with nitric acid? What happens is the NO2 part will substitute with this H, forming a compound like this. So what actually happens is nothing is being kicked off, nothing is being shifted on. We don't have any addition or elimination reactions. It's only a substitution reaction. As one thing goes off, another thing comes in, just like a football game. Now, that's literally all there is to reactions. It's mostly just substitutions. We also have something called sulfonation, which is a type of substitution reaction, but that's a bit more complex. If you're interested, you can search that online. Thank you for watching, guys. I hope you guys enjoyed. If you've got any questions, just leave them in the comments. We will reply as soon as possible. And make sure to subscribe to our YouTube channel, Meditorial, for more further videos on stuff.